some of what we've been doing. Okay, we were talking about the principle of mathematical induction, which says that if a statement about the natural number k is true when k equals 1, and it's true when k equals k plus, when n, let me start again. Suppose you show by direct computation that it's true, I'll use n, when n equals 1, and then you say, okay, suppose it's true when n equals k, now step it up to k plus 1, prove on the basis of the inductive assumption, on the basis of the assumption that the statement holds when n equals k, prove that it also holds for k plus 1. That will lead, and I want to go over some of the homework. By the way, did I say on Thursday that pressure on a crystalline solid like ice raises the melting temperature or the freezing temperature? No, it actually depresses it, so that if you're on ice skates, even if it's below freezing, you'll still melt a little of the water, of the ice, and glide on water. But if the ice were cold enough, that wouldn't be sufficient to defrost it, and you still wouldn't be able to ice skate it. It would not be slippery. Also, as you may know, starting at 9:31 this morning, autumn started. So here's what that okay. Here's what that looks like. So here's the sun, and the Earth is tilted at about 23.5 degrees from the plane of its orbit around the sun. So in the summer here, the sun's rays are closer to perpendicular. So this is the northern. So this is the North Pole, there's the South Pole, North Pole, South Pole. So in our summer, the sun's rays are more nearly perpendicular, well, not really perpendicular if you're north of 23.5 degrees north latitude. We're at 41 degrees, so the sun is about 72 degrees above the horizon at noon around June 21st, whereas so the southern hemisphere in our summer, the sun's rays are not they're more spread out, actually, as the cosine of the angle. On the other hand, in the southern summer, it's the opposite. And so what's happened is that as we go around, what happened today at the autumnal or vernal, which means spring equinox, the center of the sun is exactly over the equator, and that causes astronomical autumn, the first day of autumn. Okay, as I said, I want to go over some homework. Maybe we should first repeat the very simple example we took a look at Thursday. And again, I don't know when, because I myself haven't been able to watch the videos of the classes. I don't know when we got cut off. So what we were proving was the inductive proof. If you saw this, if you were still there, seeing it again will probably enhance your understanding. So inductive proof that the sum of the first n natural numbers, positive integers if you like, they're isomorphic, So you can quickly add the numbers as Gauss did from 1 to 100. So here n is 100. So here's n, and there's n again, and there's n again. So whatever, you know, that mathematics, when we use the same symbol multiply often in the same context, it has the same meaning. So this n has the same meaning as this n and as this n. So if n equals 100, this formula would say the sum of the first 100 natural numbers is 100 times 101 over 2. So that comes out to 5,050. I can show you if you like. Usually these formulas come from something called the method of least squares in the theory of computation, but I can show you where this formula comes from very easily. Here, suppose we have 1, 2, 3, and suppose we're adding the numbers up to n. So before that is 1 less, n minus 1, n minus 2, and so on. Okay, now, so I've listed the numbers from 1 to n, the integers from 1 to n below the line. Now I'm going to do the same thing, but in reverse order above the line. So I'm going to put a 1 there, 2 there, 3 there, and going to eventually get up to n here. So this will be 1 less than that because I'm increasing now as I'm going from right to left to n minus 1, 1 less than that, n minus 2. And notice that the sum of the pairs of numbers above and below the line is always n plus 1. Over here we have n plus 1. Over here we have n minus 1 plus 2 is n minus 1. Here we have n minus 2 plus 3. Is n plus 1. So n minus 1 plus 2 is n plus 1. Over here, n minus 2 plus 3 is n plus 1. Over here, we have n minus 2 plus 3 is n plus 1. Likewise here, n minus 1 plus 2 is n plus 1. This is n plus 1. And so here we have all these are n plus 1s. So here's one of them, here's another, and there are n of them. There are n of these sums n plus 1 for a total of n of means times n plus 1. But that is the sum of the first n plus the first n natural numbers counted twice, once above the line and once below the line. So 1 plus up to n, and many of you, let me do this, many of you know the summation symbol. It's a Greek capital letter called sigma, which is S. So this is, say, you use something called an index, say I, where I goes from 1 to n. And often it's just written summation from 1 to n of I. And that means, well, I've already written it over here. It means this. So get rid of the definition. I've already defined it. So since this n times n plus 1 counts the numbers from 1 to n twice, the sum of the numbers from 1 to n just once would be 1/2 that. 1/2 n times n plus 1, or using the definition of multiplication of fractions, it's often written n times n plus 1 over 2. So let's, so that's how you can derive that. And let's again go through the inductive proof. I've already written inductive proof up here, but let's start the proof here. An inductive proof, obviously, is a proof based on the principle of mathematical induction. So sometimes just to see how it's going, I mean, you don't need all these. So all you need is one. Show that it's true, which we did last Thursday. Show that the formula, which is just above this, the 1 plus 2 plus et cetera up to n equals n times n plus 1 over 2. So that's true when n equals 1, the quote sum of the first natural number is just 1. And then if you put 1 into that formula, you get 1 times 2, which is 2 divided by 2, which in fact is 1. But sometimes you might want to see how it's going or convince yourself further. So you might try it when n equals 2. Okay, so when when n equals 2, we have 1 plus 2 should equal, question mark, should equal. So now this is n, right? N is the, over here, it's the last number that you're adding. So n equals 2. And so in this formula that I have in a box here, instead of n, it's 2. Instead of n plus 1, it's 2 plus 1 over 2. And of course, we see that is 3, check. Yes, 1 plus 2 does equal 3. Okay, so that's step 1. And now we have the inductive assumption or hypothesis. Suppose the proposed formula holds, that means it's true, when n equals, say, k. Now, some books just use n, and then they say, okay, now step it up to n plus 1. But I don't really like using the same symbol first to mean one number and then to mean the next number, and then you're proving it for all. So I'll use a different number like k. And so what does the formula say when n equals k? It says, over here, what's in the box above, it says 1 plus 2 plus et cetera plus k equals k times k plus 1 over 2. All right, someone unmute yourself and say something so I know you're still there.
We're here, Professor.
Professor. Okay, thank you. Thank you for that reassurance. I should probably check periodically the way things have been going. Okay, so all right, so that's what the formula says when n equals k. Now for the inductive step, the step up. Show on the basis of the inductive assumption that the formula show that that formula holds or still works or is true for the next number when n equals k plus 1. Okay, so in the box above it, it says, 1 up to k is k times k plus 1 over 2. So we want to show that formula holds when n equals k plus 1. That is, what are we trying to show? We're trying to show, so this formula, 2 boxes above, says 1 plus up to n. The sum of the first n natural numbers is n times n plus 1 over 2. Now we want to show that when we take the sum of the first k plus 1 natural numbers, that is 1 plus 2. What happened? This line doesn't belong there. I'll erase it. Okay, so we want to prove that this formula 1 plus 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 up to n equals n times n plus 1 over 2 is valid when you replace, over here, when you replace n by k plus 1. There's no mystery about this. Replace n by k plus 1. So over here, over there, you're going to go up to k plus 1. All right, so we have 1 plus 2 plus 3 plus k plus 1, but we know something about what happens when you go up to over here, when you go up to k. So in order to be able to use that, let's observe that before we get up to n equals k plus 1, right before that we have n equals k plus, it's too far away, but we'll put it next to it. Plus k plus 1. So look at this part, which I could put into parentheses, but I won't. So we want to show that this formula is valid. That is, let's put in the word show. What do we want to show? We want to show that 1 plus 2 plus 3 plus 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 up to k plus 1, but k comes before that. So we want to show that that equals, right? So now we go back to this formula, this expression over here. So what does that say? This says n times n plus 1 over 2. What does that say when n equals k plus 1? So what do? You replace n by k plus 1. So we want to show that the sum up to n, which is now k plus 1, we want to show, so go back to this box here, that equals n, but n over here is k plus 1. So we want to show that this sum from 1 up to k plus 1 equals, here's the expression we want to show it equals. So instead of n equals k plus 1 over here. So that'll be k plus 1. And going back to this box up here, the next factor is n plus 1, but n over here is k plus 1. So it's k plus 1 but then up here we have a +1 in there, in the parentheses, +1 over 2. That's what we want to show. So again, it says show, over here, show using the inductive assumption that this formula, which I have in a box above, is valid when you replace n by what it's replaced by, k plus 1. When you do that, you get this last expression, parentheses k plus 1 times k plus 1 plus 1 all over 2. Let's show that that's valid. So let's start computing. 1 plus 2 plus and so on, plus, I'm going to put in the k because this is something we know about, plus the k plus first term. And by the inductive hypothesis, I'm purposely using hypothesis and assumption interchangeably because they are used, hypothesis, we can replace that whole thing by, if you look at the inductive assumption, the inductive hypothesis in step 2, above this in a box, look at that. It says 1 plus 2 plus ... plus k. That's exactly what we have here. Equals can be replaced by k times k plus 1 over 2. And then we still have this additional term here, plus k plus 1. And we want to show that that equals, just above this first box here, equals k plus 1, there it is, times k plus 1 plus 1, which is k plus 2. So this is obviously k plus 1 times k plus 2 over 2. Okay, so we're up to this now. And the way I did it Thursday was to observe, maybe we should do it both ways in case you don't notice this. Look, if you put this into parentheses, which you're allowed to do, we see that we have a common factor between these two terms. Of k plus 1, right? There's a k plus 1. I don't want to mess up this up too much. See, if I were at the board, I could point instead of writing on it. So we have k plus 1 here. I don't know, maybe if I did it in a different color. Yeah, let me try. I never tried using the highlighter. Let's see. I don't know, can you see that yellow there? I guess you can. Okay, so, okay, we have a common factor of k plus 1. Let's extract it and write k plus 1. Well, that's good right there because we want to show that it equals k plus 1. You know, keep an eye on what you're trying to get. And when you take that out in the first factor, in the first term, you're left with k. And the complementary factor here, there's no other factor written, so it's understood to be 1. So it's it's k plus 1. Oh, so, okay, so when wait, what is, so I want to show this equals k plus 1 times k plus 2 over 2. Okay, so I have to, let's get so we're adding these two fractions. Let's get a common denominator. Yeah, okay, so taking out k plus 1, we have k over 2 plus 1, right? Again, the complementary factor of the second k plus 1 is 1. And so this is k plus 1. And now we need a common denominator, so that's k over 2 plus 2 over 2. So we can now add these two fractions and be left with k plus 1 times k plus 2 over 2, which is, again, so this is over 1. So you multiply numerators, you multiply denominators, and in fact, you get k plus 1 times k plus 2 over 2, which is exactly what we wanted to get over here. Now, of course, if you don't notice that you have a common factor here in yellow, alternate. So we have 1 plus, etc., k plus 1 equals, again, that is going to be, by the inductive assumption, k times k plus 1 over 2 plus k plus 1. Okay, so if you don't notice that you can take out a common factor, you can just proceed and do what the formulation tells you to do. So in the first fraction, we have k times k plus 1. So we'll multiply that out and get k squared plus k over 2. And then in order to proceed with the arithmetic, we need a common factor. So this is over 1. So I'll have to put it over 2 and multiply 2 into the numerator. And so you get 2k plus 2. And you have to extend your fraction line to go under the entire numerator and over the entire denominator. And so now we have a common denominator. So we preserve the denominator and add the numerators. And when we do that, we get k squared plus, so here we have k plus 2k is 3k plus 2. And so, I mean, the advantage of taking out a common factor is it's just easier. You avoid the multiplication and you avoid the factoring. But okay, so this, as I said, this nothing more than first year algebra here. You should be able to factor that. But you know what? You have a clue as to how it should factor. Let's see if it does, because we know what we want it to look like. We want it to look like this or this. So let's see. All right, so here we have a trinomial. So we'll open provision for two binomials, and we have k squared, so that'll be k and k, and everything is positive, so that's plus and plus, and 2 is a prime number, so it factors into just 1 and 2. And you should always check factoring by multiplying back, using the acronym FOIL, right? You know that, right? First, outer, inner, and last. And sure enough, that does equal k squared plus 3k plus 1. The reason you always have to check factoring is you might do it in what looks like a correct way, but isn't. For instance, suppose we try factoring, say, x squared plus 1. Let's make it a trinomial. Suppose we wanted to factor x squared plus x plus 1.
Professor.
Yeah.
If we're writing down this, it's something that looks like this on a test, would you like us to FOIL and check it on the test?
I'm sorry, say that again. I raised the volume. I had the volume too low. I barely heard you. So something about FOIL on the test, say it again?
Yeah, so if it was very similar to this proof and we were assuming that it did factor properly, should we FOIL it out on a test to show that it actually works instead of just assuming we got it?
No, you should factor it for your own purposes to make sure it's correct. But no, that's not part of the question, so you wouldn't have to.
Okay, thank you.
Okay, so how would you factor this if you could at all? Let's try factoring that. Well, it's a trinomial, so it would factor into two binomials, and the product of the first terms has to equal the first term, so it has to be x and x, and now everything's positive, so plus, plus, and you don't have a lot of choices for 1. The last terms in FOIL, the last terms have to be 1 and 1, and if you just leave it at that, you might be satisfied, okay, I factored, but no, if you check, so what I'm saying is, if you could factor this, the only way to do it x plus 1 squared, but this is not a correct factorization. So it's the only factorization, or the only, let's say, possible factorization, but it's not a factorization. So what does that tell us? It tells us that it can't be factored. So x squared plus x plus 1 is not factorable.
Professor.
Yeah.
Sorry. When you start typing that line, if you could factor x squared plus x plus 2, isn't that supposed to say x squared plus 2x plus 1?
Yes, it is supposed to. No. I wanted to. No, I'm showing an example of something that's not factorable.
Okay, thank you.
So if you could factor x squared plus x plus 1, the only way to factor that, the only way to get your x squared as the first term is to have x and x in the parentheses. And the only way to multiply the last terms to get the last term is to have 1 and 1, and everything is positive. But if you check it, then you get x squared plus 2x plus 1. So if you could factor it, it would be that, but that's not the correct factorization. Why not? Because, well, you just said, when you multiply it back, I'm just making the point that you always have to check factoring. I'm not saying you have to show it, but for yourself, you have to check factoring, because you might do everything that seems right, and yet it's not right. I mean, it only seems right because you're looking at part of it. When you factor a trinomial, initially you're looking at the first terms and the last terms to get the first term and the last term, respectively, of the trinomial. But then you have to check to make sure you get the proper middle term. And here, the only possible factorization of x squared plus x plus 1 is x plus 1 times x plus 1. But when you check it, you don't get x squared plus x plus 1. You get x squared plus 2x plus 1. And so x plus 1 times x plus 1 is not a correct factorization. And so that shows us, look, if the only way to do it is to do it this way, x plus 1 times x plus 1, but it's not correct, then x squared plus x plus 1 is not factorable. But that shouldn't be so surprising, because we've already looked, and we'll look much more deeply later on. And as soon as I can, I will get you the curriculum and everything. But we are moving along in the curriculum. So we'll talk more about this later. But you already know of numbers that are not factorable, and they're called prime numbers, right? So you could call x squared plus x plus 1 a prime polynomial, but when it comes to polynomials, we usually use the word irreducible, make it n, and irreducible. It really means prime. But in the theory of equations, the word irreducible is used. It is an irreducible polynomial. I would also like to talk about recursive or inductive definitions, but I have been asking you to do some homework, and we're up to question 15 on a sheet, which again, I hope to get to you, which I've called forms of integers. So let me leave for the moment. We have like half an hour more. For the moment, let me leave. You'll have a lot more questions about mathematical induction, a lot of practice in diverse examples. But for now, and as I say, I want to talk about inductive definitions. But for now, let's maybe we should go over some of the homework that I hope you've been doing. Homework. Keeps slipping. By the way, if as I'm going along, you have a question, see, the page just moved without my touching it. Unmute yourself and ask, because, if you have a question, probably you're not the only one. So, but in addition to that, when class ends, I'll stay available, and eventually I'll establish this so-called waiting room where I can speak to you individually, maybe even with some luck, get to know you a little bit. Okay, so question 1, so 1A. Homework on, so I've entitled this sheet Forms of Integers, what they look like, how they're written. Okay. All right, so we want to show the square of an even integer is even. Let's recall from the division algorithm, an even number is expressible as 2k and odd as 2k plus 1. 2k minus 1 would work just as well, but then you have to worry about negatives. But also from the division algorithm, the division algorithm has a plus. Let's review what that says. It says that A equals BQ plus R, where 0 is less than or equal to R, is strictly less than the absolute value of B. So dividing by 2, that is B equals 2, we have any integer A can be written as 2 times some number, some quotient, plus R, where 0 is less than or equal to R is less than 2, where as usual A, B, Q, and R are integers. So any A equals 2Q plus 0, and that shows that A is 2 times something. That's called, it's not a J, it's a semicolon. That's an even number, semicolon. If you remember the definition of B dividing by A, this says that A is exactly divisible by 2. Or, so we have either A equals 2Q or A equals 2Q plus R, where R is less than, strictly less than 2. So the only other choice would be 1. And this says A is odd. So let's close parentheses here. Yeah. So, okay, so we will express an even number as 2 times some integer and an odd number as 2 times some integer plus 1. So, so suppose A equals 2k. And in 1a, over here, 1a in the homework, show that the square is even. So show a squared is even. That is, show that a squared is of the form, that's why I call this forms of integers, is of the form, it looks like it can be written as, is of the form 2 times I don't know, j for some integer j. All right, so you just compute a squared equals, here's what a is, it's 2k, so it equals 2k squared the whole thing squared, so you need parentheses, and using, elementary algebra, which, as I said, is really all we'll be using. This is 4k squared, but strictly speaking, look over here, you have to show, I mean, it's a trivial step, but, for precision, you have to show that this can be written in the form 2 times some integer, say j. So of course, okay, so this is 2. Do you remember the associative property that we had at the beginning of the term, which is now a quarter over? Today is the first day of the second quarter of the term. 2k squared, and this equals 2j if you make j equal to 2k squared. So it's exactly, here it is in a box, it's exactly in the form 2j. It's 2 times some integer, you can call it j. So remember that if a statement and its converse, so you switch the first part and the second part, if a statement and its converse are both true, then the two statements are said to be logically equivalent, because whenever you have one, you have the other. Can't have one without the other. That would be the contrapositive, which is also valid. So conversely, if, say, okay, I used n, if n squared, so the square of an integer is even, then the original integer, in this case n, and this, where we talked about indirect proofs, this would be an example of an indirect proof. Look, if n squared is even, there are only two possibilities for n itself. Either it's even or it's odd. So what you do in a situation like this is say, suppose not. Proof by contradiction. And as I think I've said, I use a pair of clashing arrows to mean contradiction. Those are two arrows pointing directed against each other. So this is an example of the indirect method of proof. So why are we using the indirect method? Well, suppose you know that n squared is even. What are you going to do? Check every integer n to see whether when n squared is even, n must also be even? No, that suggests using an indirect proof. Suppose not. So here it is, suppose not. In other words, we're supposing, well, if it's not even, it's odd, by what we were just talking about with the division algorithm. Every integer is either 2k or 2k plus 1, so it's either even or odd. So suppose not. Suppose n is odd, period. Then n can be written in the form 2k plus 1, where k is some integer. And so n squared equals 2k plus 1 squared. I mean, this is simple, but I'm showing it in great detail so that you thoroughly understand it. And then to square a binomial, you square the first term, you get 4k squared. You take twice the product of the two terms, you get plus 4k, and you square the last term. So write that down if you don't know it. Precept from elementary algebra: to square a binomial. Okay, to square a binomial, square the first term, take twice the product of the two terms with the signs, and square the last term. The reason you take twice the products of the two terms with the signs is, remember our definition, if you have a minus sign there, by definition, that's plus the negative. So you're using the rule for multiplication of signed numbers. But look, so what do you try to do with the indirect method? You try to get a contradiction. So we're given that n squared is even, and now we're supposing that n is not even, supposing it's odd, show a contradiction. Well, what's the contradiction to saying over here n squared is even? The contradiction would be n squared is not even, n squared is odd. So we want to show that n squared, here it is, n squared is not even, but in fact is odd. And to do that explicitly, so, you know, if you're not careful in mathematics and do all the steps, it can very easily get away from you, get out of hand, and you lose track of what you're doing. So we have to explicitly, not just looking at it and saying, oh yeah, that looks like an odd number to me, yeah, it's a +1. We actually have to show that it has the form of an odd number, which I'll put down somewhere back here. An odd number by the division algorithm is, wherever it is, over here. An odd number has to be of the form 2k, 2 times some integer plus 1. And okay, it's not difficult, we can do that. So 2 times 2, we have to take out a 2, 2k squared plus 2k plus 1. And so you can call this j if you like, say 2j plus 1. But how do we know we can call that j? Well, you know, it's not just because it kind of looks that way or it should be that way. No, there's something really explicit in the mathematics that we've been building up. And that's something, those two specific things are the rule for closure of the integers. So k is an integer. So by closure under multiplication of the integers, k squared is an integer. By closure under multiplication, 2k squared is an integer. By closure under multiplication, 2 times k is an integer, because an integer times an integer is an integer. And by closure under addition, the sum of 2 integers is an integer. So that's what, not just because, you know, quote, obviously, you want to avoid saying obviously in mathematics for the most part. No, what's actually operating there is the closure principles that we had at the beginning when we talked about the properties of an ordered integral domain. And what's the significance of that? The significance is n squared turns out to be odd, contradicting the given fact that n squared was even. And since, as I've mentioned before, I'm not going to take time to prove it, it's easy enough with truth tables. You can't have a contradiction in any mathematical or logical system. If you do, then every statement is true and every statement is false. And to use the name of a book written by an African Nobel Prize winner in literature a few years ago, things fall apart. Things fall apart. Not that I read the book, I'm not that literate, but I thought it was an interesting title. So to avoid that contradiction, you have to dismiss, get rid of the possibility that we suppose that n was odd over here, but no, that led us to a contradiction. So that was a supposition. Again, you can suppose anything you want. It may not be true. You can suppose that it's, I don't know, January now. Doesn't make it true. You can suppose whatever you want, but if that supposition leads you to a contradiction, then you have to throw it out. You have to dismiss it. You have to say, no, that can't be right. So we have to dismiss the possibility that over here that n is odd. And conclude that n is even. And then again, you should conclude a proof by saying something like, that's what you wanted to prove. And so, as it says, 1a and 1b together say that a number's being even is logically equivalent to its squares being even. So if n is even, so IFF, if and only if n squared is even, n is even, and conversely, if n is even, n squared is even. And from that, if you look at it, we've essentially already proven 2a and 2b in 1a and 1b. It says the square of an odd integer is odd. So how would you prove that? Assume not, assume it's even. But in 1a, we proved that the square of an even number is even. So the square of an odd number can't be even. Again, look at 1a. 1a says the square of an even integer is even. So in 2a, you have to prove that the square of an odd number is odd. No, it can't be even because the square can't be even. We just proved that in 2b, we proved that if the square is even, then the number itself is even. And conversely, if n squared is odd, n must be odd because in 2a, if it's even, n squared is even. You know, you can use that. Next time I'll give a much more expeditious proof of this. We can use those facts to prove, we'll do much more than this next term. We'll prove that the nth power of any non-perfect nth, and that the square root of any non-perfect square is irrational, and in fact, more than that, in the same way, the nth root of any non-perfect nth power is irrational. But for now, let's just do it for the square root of 2. We can use this to prove that the square root of 2 is irrational. And again, irrational means not rational, and rational means, we've mentioned this before, that it can, a number is rational if it can be expressed as a ratio of two integers, the second one not zero. So we can prove that the square root of 2 is irrational. And the Greeks knew this. They were kind of horrified by it. They didn't appreciate knowing that numbers could behave so erratically. They like to think of everything as usually being simple whole numbers, or at least ratios of whole numbers. But they were able to show that the square root of 2, that's a number which squares exactly into 2, which I mentioned before. You can get close to it, as close as you want, but you can't actually get there, as a quotient of two integers. As a quotient of two whole numbers. And the Greeks were mortified by this. They did not like that at all. So, by the way, someone say you're here, if you're still here, as it approaches 7 o'clock.
Just here
Yes,
still,
we're here,
Professor.
Professor.
Oh, all right. Whoa, we're on a roll here. We may actually finish the class intact. Okay. So we can use that to show that the square root of 2 is irrational by contradiction. What does contradiction mean? We will assume, again, you can assume or suppose anything you want. It doesn't make it right. And if it leads to a contradiction, in other words, if I don't make any other mistakes, and this is the only possibility for a place where we get to a contradiction, then we have to throw this out. We have to dismiss it. We have to say, no, this assumption is wrong. Assume that the square root of 2 can be written as a quotient or ratio of two whole numbers, integers. Let's write the fraction in reduced to what's called lowest terms. What does it mean to say a fraction is in lowest terms? For instance, why do we say that 2/3, 2 over 3, is reduced to lowest terms, but say 6 over 9, 6 over 9, or I don't know, 10 over 15. Why is 2 over 3 in lowest terms and 10 over 15 is not? So we say a fraction is in lowest terms when we talked about divisibility, divisors, when there's no common divisor, well, more than one, between the numerator and the denominator. So for instance, 10 over 15 can really be written as 2 times 5 over 3 times 5. And we have a common factor in the numerator and the denominator. And by the definition of multiplication, this can be broken into two separate fractions, 2 over 3 times the fraction 5 over 5. But by the definition we had of divisibility, 5 divided by 5, we find that this is 1. So it's 2 over 3 times 1. And since 1 is the multiplicative identity, this is just 2 over 3. So we call this fraction in reduced form, and not reduced, not in lowest terms. So you can always reduce a fraction to lowest terms. We'll actually prove that next term, where we'll prove that 2 and 3, we'll talk about this term also. 2 and 3 are called relatively prime or prime to each other. And so if the numerator and denominator have no common factors, no like 5 over 5, then we say the fraction is in lowest terms and the numerator and denominator are relatively prime. So we'll take a look at that. For instance, 6 and 35 are not prime numbers. 6 and 35 are not prime numbers. They're factorable, but we'll talk about this later. They're called they're said to be prime to each other or co-prime in that they have no common factors. So anyway, suppose A over B, where A and B are integers and A over B is in lowest terms. So if any of that is contradicted, we have to throw out the possibility that that the square root of 2 can be written as A over B. And again, you can always reduce a fraction to lowest terms by getting rid of the highest common factor in the numerator and denominator. So I'm not going to make any, hopefully, I'm not going to make any mistakes in this computation. The only source of a possible contradiction is the assumption. And, well, that may not be right. And if we get a contradiction, it can't be right. And if nothing else is wrong, then that has to be wrong. So squaring both sides. So to square a fraction, you square the numerator and denominator, because it's A over B times A over B, equals, and by the definition of the square root of 2, that's precisely the number which when squared gives 2. And getting rid of fractions, we can say A squared equals 2, this 2 times B squared, displaying A squared as what? A squared is 2 times an integer. B squared is an integer by closure under multiplication, displaying A squared to be an even integer. But from 1b above, if A squared is even, A itself must be even. So A equals, say, 2k. So A squared equals 2b squared over here, A squared equals 2b squared, becomes, since A equals 2k, A squared becomes 2k squared equals 2b squared, or 4k squared equals 2b squared, or dividing both sides by 2, 2k squared equals b squared, showing that so over here, this shows that b squared is even, and therefore, again, by question 1b, b itself is even. So there exists some, I've used k, I don't know, q, it's this an integer q, such that, the colon means such that b equals 2q. Oh, b equals 2q and A over here equals 2K. So A over B equals 2K over 2Q, which is what? Not in lowest terms. And so to avoid that contradiction, we have to conclude that our supposition that A over B, that the square root of 2 can be written as A over B, is wrong. We conclude that the square root of 2 cannot be written as any rational number A over B, because if you could reduce it to lowest terms, but then we found, nope, it's not in lowest terms. So again, I've said this before, people who just sort of glibly say anything is possible. No, not anything is possible. And so this leads to, as some of you know, much more in mathematics. It introduces, it shows that there's a whole new set of numbers that are not rational numbers. And as some of you know who are taking or have taken 4010, advanced calculus, fundamental analysis, there are actually more numbers that are irrational than rational, which may really be surprising because there's an infinite number of rational numbers. I mean, there's even an infinite number of just plain integers and certainly fractions, but it turns out, and we won't go into this here, I refer you to 4010 for this, that there are no more, even though there's an infinite number of rational numbers between, you know what, I'm not going to write anymore, it's 10 after 7, so let me get back and at least see you for a few moments. And I don't know if you necessarily want to see me, but I will turn the camera on. So let's see, and then zoom, and then stop broadcast, and press that, and okay. Go back to my video, and then stop recording.
The recording has stopped.
Okay, the recording has stopped. Okay, so so what I was saying was that okay, now I can sort of see everyone. So what I was saying was that even though there's an infinite number of rational numbers packed in to the open interval between 0 and 1, right? There's a half, a 1 over 2, 1 over 3, 1 over 4, and that's just an infinite number of rational numbers between 0 and 1 whose numerator is 1. Then start with all of them without duplication, avoid ones that don't reduce to ones that you've already had. There's an infinite number of rational numbers between 0 and 1 with numerator 2, and so on. So it looks as if there are many, many more rational numbers than there are integers, because the integers form a discrete set with 1, 2, 3, and so on, whereas the rational numbers form what are called a dense set, meaning between any two rational numbers is another rational number. So it looks as if there are infinitely many more rational numbers than there are integers, but guess what? And you don't have to guess if you've taken Mathematics 4010. We're not going to go into this now, but I'll just mention the horrifying, unbelievable fact that, and Cantor, when he discovered this, didn't believe it himself, but you can show it. It's not all that difficult. It's not part of this course, so I won't do it. someone wants to stay, I can show it to you. But you can show that there are no more rational numbers when you take all of them, not just the ones between 0 and 1, but when you take all the rational numbers and all the integers. In fact, there are no more rational numbers than there are integers, but there are more irrational numbers, such as the square root of 2, and even worse than that in a sense, pi and e, basically natural logarithms. There are way more irrational numbers than rational numbers, to the extent that compared to this, and the real numbers consist of all rational together with the irrational numbers, and there are so many real numbers, in other words, that aren't rational. There's so many irrational numbers that compared to the entire set of real numbers, rational numbers, even though they're dense, rational numbers don't exist. That goes into a part of mathematics called measure theory, but I'll just give you an application of measure theory to probability there. If you point to a number on the number line, the probability that you will point to a rational number is 0. When you have an infinite sample space, it's possible to, could you point to a rational number? You could. Nevertheless, the probability is 0. So when you have an infinite sample space, it's possible to have something that can happen even though the probability is 0. And likewise, it's possible for there to be a 100% probability of doing something, and yet it might not happen in an infinite sample space. For instance, instead of real numbers, if you point to a specific number, there's a 100% probability that it will not be a rational number. Could it be? It could, but the probability is